I mean, I've already introduced myself. I'm Phill Gilbert. So I sit in the 3-part division specifically, but I'm HP storage, like everybody else is here. HPE storage, like everybody else is here.
Make that mistake.
Yeah, you know, I haven't got that wrong in like 3 years, and then I've done it twice in 3 days. Perfect. So I'm technically responsible for the software stack that sits inside 3-part, but I spend a lot of time looking at the futures of what our entire portfolio does to make sure that everything that we do ties together. Because the one thing we don't want, I mean, we've already talked about putting things into silos. The last thing we really want is to start developing all the different technologies in silos as well, because that leads to a very kind of strange experience for our customers. So when I look at the kind of the world as it is today, we have 3 kind of big trends that are going on from a storage perspective. One's this kind of constant march on towards density, and I naively assumed that with all flash, people were kind of quite happy with the density we had, and then I had a number of customers who came to me recently and said, we're trying to get even more density. We want to get 4 petabytes in a single rack U, that kind of thing. So that's the kind of density they're looking to achieve. And there are challenges as to how you actually achieve that kind of density, because there are upsides to that in that you can, you know, massively reduce your footprint if you are after those kind of capacities, but there are also issues in that if you want to achieve those kind of capacities, you have to look at very, very, very high capacity drives. And that means that each drive offers a relatively low amount of performance compared with the amount of capacity that it delivers. Even last year, I think it was, at the Flash Memory Summit, there were 60 and 100 terabyte drives that were kind of tech previews, and they were pretty thick, standard small form factor drives. But the performance they offer is roughly the same performance as we have today on 2 and 4 terabyte drives, but they are 50 times bigger, and that obviously has a performance issue associated with it. So while we strive towards this density, we have to make sure that we don't sacrifice performance that everybody requires in the same kind of time. And that kind of leads on to the next point in performance, in that on the flip side to these customers who are after extreme density, there are also a different category of customers, or even customers with different requirements that require this kind of extreme performance, and even higher than all flash arrays can deliver today. Now, that's not every customer, but there are enough of them that it really does make a big difference, and it's something that we have to make sure we're always delivering, you know, always on the forefront of performance. And we can't forget that just because we're in the world of all flash, that there are still these increasing performance demands from a set of applications, some of which Omar's already kind of covered. Now, the last one's AI and machine learning, and that's kind of interesting, and it's a trend in the industry from a storage perspective, but also a trend in the industry at large, from everything from self-driving cars and kind of onwards. But from us, there's a big push in terms of AI and ML, from not only from the InfoSight perspective, but also from each actual array, each component in the data center becoming more intelligent and more aware of what it is and what it does. So we have a load of things going on here. Now, the kind of thing that's interesting is that the medias that we have had recently, whether that's NAND media or whatever it might be, and the protocols that we have today, which are generally in the storage industry, SATA and SAS, are no longer capable of delivering what it is that we actually need to provide the performance and capacity that we need. So there has to be a generational bump, not in only the underlying media, but in terms of the actual protocol as well. Now, there's a huge amount of focus today on NVMe, and so I wanted to take just a moment to cover the difference between the two. SAS has been around for quite some time now. I remember being introduced, that must have been sometime around 2006, 2007, I would guess. And when it came out first in servers, so they were the first to pick up SAS. And SAS built on top of the original SCSI protocol and delivered serial access to an existing parallel protocol. So it delivered a point-to-point access from a controller to a given drive, and that massively increased performance. It meant the days of kind of ribbon cables and those kind of things were over, and I think everybody who's ever used ribbon cables will be very pleased that those are a thing of the past. But the thing that was really important about it was that it's this kind of point-to-point access, and you can see here the kind of point is that we have this SAS controller that sits on a PCIe bus, so it directly connects to the CPU, and that talks to the underlying drives. There can be switches and fabrics and things in between, But the idea is that you have this kind of this middle point that does a conversion from PCI that the CPU is talking down to the underlying media. Now, as I said, it's got better and better, and we don't have daisy chains of drives and those kind of things anymore. But the protocol is still an evolution of SCSI. And SCSI was built for spinning drives. So SCSI has lots of commands that are specific to spinning drives. Even really basic stuff like spin up and spin down to tell the drive when to actually turn on and when to turn off. Gathering telemetry, talking about cylinders and heads and all kinds of things that are to do with physical media that spins and moves. But solid state media doesn't have any of that. Now, to fit into SCSI, some of those drives have emulated parts of that kind of those kind of paradigms to allow them to talk over SAS. But what would make more sense is to actually move to an architecture that is built specifically for solid state media, and kind of just leave all that stuff behind, so we don't have to worry about it anymore. And that's where NVMe comes in. So NVMe is non-volatile memory express, and it is a NVMe actually largely defines a protocol, a language that you speak, but it changes the architecture, the physical architecture in the system as well, because it leaves behind all the SAS stuff. So the obvious thing to notice is that that color that's kind of gone a weird orangey that's supposed to be red, that is the SAS infrastructure that kind of sits between the drives and the CPU. On the NVMe on the right, you have the CPU and the PCI controller, and those two generally today are synonymous, but the drive's NVMe controller is directly attached to the CPU via the PCIe controller. So that means that unlike SAS, where you're going through this kind of conversion layer, you don't have any of that with NVMe. NVMe is obviously much higher performing because it's delivered over PCI Express. So there's no, like when we talk about SCSI, we talk about fiber channel, we talk about both the physical media that it passes over as well as the language that's spoken. With NVMe, there's not such a strict definition of the underlying physical architecture, and instead it's more talking about the language that you speak. Now, the first implementations of this were based on PCIe. So your phones, your laptops, they all have PCI Express in them as a general rule of thumb. It's much more efficient. It actually reduces costs because for people who are building things like laptops, you don't have to include SATA controllers and all the stuff that goes around with them. It narrows down the driver scheme, so it makes just theoretically improves the performance of your OS, and everything should just get kind of bigger, better, and faster, as well as cheaper, and it enables slimmer laptops because you've got smaller sets of hardware in there. So there are a lot of advantages to this approach, and as with SAS, it came to serve as first because it's the easiest implementation. It's the kind of most lightweight place to put new technologies. Now, the one difference between these two that is kind of subtle to pick up is this different differentiation here between NAND and SCM. And that's an important context because one of the things with SAS is that SAS can only speak block. You can only have a drive at the end of it. That is the language that it talks. It's designed specifically for storage applications. And NVMe, that's not strictly true. And I'm going to touch more on the importance of that one, but I just want to make sure I kind of bring that one up. So NVMe is kind of going to be essential. And you can see that because it is largely replacing SATA. In laptops, phones, as I said, SATA is basically dying as a protocol, and it's being replaced by NVMe. It's cheaper and it's faster. And I say it's cheaper, the big reason it's cheaper is that as more and more people shift towards it, sort of the whole point in volume is that as people shift there, the prices come down. SATA becomes essentially like a niche protocol now because most people don't use it anymore and the prices go up. So you kind of have this tip in the balance when NVMe becomes actually cheaper to deploy than SATA. And that kind of thing is going to happen with SAS as well. As NVMe replaces SAS, the enterprise NVMe drives that are required for things like storage arrays are going to reduce in price, and the SAS ones are going to go up in price, and there's going to be a tip in the balance, and there will be a point at which NVMe is cheaper than SAS. It's not right now, but it's going to happen pretty soon. So NVMe is really, really important for the future of what we're doing because it does strip away all this stuff to do with spinning media that we just kind of want to leave behind in the past. But NVMe is really, I'm going to insult people here, but it is plumbing. It is a way to an ends to a mean. By itself, NVMe delivers for NAND media today relatively low benefits. It's a pretty big shift from an architecture perspective, especially when you're talking about re-architecting something like a storage array to take advantage of this. And in reality, the benefits that we get from it are pretty low. It's not really much higher in terms of bandwidth when we're talking about NAND media. It's a bit lower in terms of latency, but it's not changing the world. It's not like going from spinning media to SSD. It's not that kind of change. but it enables something different. Now, when we look at drives today, and the important thing here is the kind of line chart, the arrow really. What I'm getting at here is that when we shifted, and this is why there's a big difference between hard drives and spinning solid state media, is this red part over here. This is the actual media inside a drive. So if I've got an SSD or if I've got a spinning drive, whatever it might be, the media contributes a certain amount of latency to how long it takes you to actually get data from the drive. Very important for transactional workloads, SQL, that kind of thing. When we move to SSDs, that drops down significantly, and you can see on the right-hand side that they're significant. Now, this isn't to scale. There's a little arrow at the top. Hard drives are significantly higher than SSDs. But the important thing that I'm trying to pull out from here is that that's the same on SATA SAS and NVMe. These two over here are the controller and software. So those are the architectural bits that go with the media. There's an actual controller that sits on the drive that has some overhead, and there's a bit of software that you have to have in the operating system to speak to whatever that device might be. Now, in the case of SATA, the controller overhead is pretty low because SATA controllers are very simple, and the software overhead is higher because this operating system has to do more. In SAS, it's flipped. SAS controllers are much more capable, so the OS does less, but then you incur a higher controller penalty. NVMe, those two are both much lower because NVMe is so much more streamlined, and because you're essentially talking directly to the CPU, you don't have to go through an expensive software stack. But in reality, and this is kind of what the white line is showing you, it's incremental benefits when you're talking about NAND, because the thing that contributes the most latency is not the software and it's not the controller, it's the actual media itself. Nobody's actually said anything against me yet, so obviously I'm not saying anything controversial enough. Now, the important thing when we talk about NVMe, really, is not what it can do from a storage perspective. Storage is interesting. It allows us to do laptops, tablets, phones. It allows us to put SSDs in the front of arrays. It means we can talk end-to-end, simplify things, and get a little bit of latency improvement, potentially free up some CPU cycles, which is kind of nice, but nothing huge. But when we start looking at the next set of media that goes behind NVMe, then you're talking about something entirely different. So I don't know if you guys have heard about SCM, storage class memory. One of the biggest, the most famous implementations of that is the 3D crosspoint technology. That is branded by Intel as Optane, so that's the technology they have got out today. It comes out today as a PCI Express form factor, so it's a card that you install directly on like a system board, for example. But the form factors of what are called U.2, so standard 2.5-inch small form factor drives, they're coming out pretty soon. These are not SSDs. They look like SSDs, and they can kind of pretend to be SSDs, pretend to be an actual storage device. But these devices are not really SSDs. They just emulate being a storage device. They're actually memory devices, and you can talk to them in the same way that you would address memory. So when you address a storage device, you talk block, you talk pages or blocks or whatever it might be, and you address that directly as a storage device. That means the CPU can't access directly the storage device. It has to go through a software layer to be able to talk to a storage device, and it has to make requests, storage requests, to be able to pull data out of that storage device through a software stack. Storage class memory is very fundamentally different. It behaves far more like DRAM. It is directly accessible by the CPU as memory. And that's very different, because that means there are no software stacks. It means you don't have to go through any of the kind of the standard layers of going through these things. It means that the CPU wants to store some data, it can stick it in an SCM device like it would with memory, like a running application in your system, can write it to an SCM, read it to an SCM device as memory in byte addressable mode. And that's fundamentally different. Now, that kind of thing you cannot do with SAS, because SAS is a block protocol. It defines how to speak to a block device, and everything is block. But NVMe kind of has two modes. It has block mode, and it has memory mode. And in memory mode, you can talk to an underlying device like it's memory. The big thing with SCM, the big thing that makes it different from DRAM is that it's persistent. So in the event of a power failure or anything like that, the data is not lost. Now, that's a huge shift, because that means in today, if I power off my laptop right now and turn it back on again, it boots it back up again. It has to, because the There's nothing in memory. The memory is wiped every time my system turns off. But if I had SCM on there and I powered off my laptop and powered it back on again, it could come back in exactly the same state, ready to rock and roll exactly as I left it, because the memory is not wiped. So it is persistent memory. And this kind of concept has never existed before. It is literally brand new for us. So it opens up a whole new world of opportunities to be able to use this in a fundamentally different way to reuse storage devices today. Because you don't have to write data across them like you do SSDs. You don't have to do any of the kind of traditional work. And when we look at it from a performance profile, it sits way down close to DRAM and much closer there than it is close to the NAND media. So that means that not only does it behave like a memory device, but it has as good as the performance of a memory device. So now I have a memory device sitting on a memory controller directly attached to my CPU that is persistent. So I don't have to worry about, in the event of a power failure, how do I get data out of it? How do I store that down onto the drives? They're also huge. So your average memory DIMM today, 16 gig, 32 gig at the top end, but you're going to be paying like crazy money for those kind of things. These devices, the initial versions are 375 gig. There's one that's around 750, and there's one that's 1.5 terabytes. So these are huge devices that sit on the memory bus that I can just write to as if they were memory, and I don't have to worry about protecting them in the event of a power failure. Does this all make sense so far? Awesome. Feel free to hit me with questions.
What are you guys going to make a server run on the CPU network and RAM slots?
Oh, well, that's a good question. So today, this doesn't exist in a DRAM form factor, but it will do very soon. So once it exists as a DRAM form factor, not only is it a memory device, but it actually sits on the CPU's actual memory bus. And that means that you can do some really crazy stuff with it. But you have to have applications and operating systems designed to use it, because they're not currently able to.
As the storage gets faster and gets closer to the core, you have a larger differential between the storage tiers. You know, it's like jet speed down to your driveway.
Yeah.
So how does that challenge be addressed? And this is great. This is good news. So you've rewritten the whole industry has rewritten the algorithm to access data. They've rewritten the limitations over, wider bus paths.
Yeah, absolutely.
Beyond 5 gigahertz is what you're getting
It's not a gigahertz race. It's a matter of data path width. So NVMe destroys, all the paradigms now about parallel processing, multiple cores, those type of things. So, what trends are we looking at to address those type of things?
So there's a number of issues that this pushes a lot of the performance boundaries that we have today. From inside the array, we have things like PCIe and we have things like NVMe that address those. From a performance perspective externally, if you've got an array that has, let's say you take the extreme example of we have an array that has CPUs and it has nothing but SCM devices sitting on a memory bus. So it's kind of crazy fast. Then you put that with iSCSI or Fibre Channel on the front end, which is an architecture built for storage media and spinning media originally, and all of a sudden you just put a crazy bottleneck in the middle of an extremely fast system, because both ends of this are pure PCI Express, and then what you've got in the middle is the kind of almost an archaic storage fabric. So that element has to change as well, and that's where we're going to start seeing a whole new set of protocols sitting in there. At the moment, the front runner is NVMe over Fabric to sit on the fabric to provide a way to get access to this access, but it's not by no means a kind of done deal. It is the front runner, but there are a whole lot of other protocols sitting out there as well. There's iWarp, there's a whole ton of RDMA-based protocols out there. Now, I say NVMe over Fabric is the front runner. It is working as a proof of concept. There's a couple of vendors who support from a switch perspective, and it has been demoed by another storage vendor as working, but it has a number of issues today, like failover, in that if a path fails, it's just gone. So you can't fail over like a volume between controllers and that kind of thing. So it's not mature from a market perspective. So it is more a proof of concept at this kind of stage than anything else. But once we look at those kind of technologies, what we're really looking at is a whole shift from front end to back end. But changing your entire infrastructure is really hard. I think you're going to ask a question.
Yeah, so is this something that HPE Labs is also looking into, since they're already doing like photonics with the memory I mean, it's kind of falls into the same.
Yeah, it absolutely does.
Scenario.
And if we look at everything from the machine through to the Gen Z kind of consortium and all the technologies in there, a lot of this comes from those concepts. And I've been asked recently twice about Gen Z, so I don't know if you guys know what Gen Z is. It is a shift in the paradigm of compute where since ever, our whole world has been CPU centric. So we have a CPU, we attach memory to it, and we attach storage devices underneath, and that's kind of the way the world lives. But there are scale limitations associated with that because your CPU is essentially your system is only as fast as your CPU goes. And you can connect two together, but that's never really as efficient as having two actual CPUs that were almost working as one. Gen Z and the machine kind of flip that and instead build a world that is memory centric. So you build a huge pool of memory and then you attach like a ring of CPUs around the outside. So it shifts the whole kind of concept of how compute works to give you a far more scalable system. And imagine like a data center full of racks and all those racks are one machine. That's kind of the goal of where we're going with these technologies. Now, that is a fantastic dream, and I'm not saying we're never going to get there, but in order to move to those kind of technologies, you've got to rewrite everything. You need new operating systems, you need new applications, new services. The world has to change fundamentally to take that on. And you won't be able to just lift and shift your existing applications because it's a completely different architecture. But what those places do give us today is the same thing that kind of Formula One gives us for cars today. We don't drive around in Formula One cars. It'd be nice, but you can't. But a lot of the technologies that are built in Formula One end up in cars, everyday normal driving around cars, because it's a way to prove a technology. It's a way to kind of to play around with something before we work out how to put it in real cars that we're going to drive every day. And Gen Z and the machine give us the same thing. They give us a place to play around with these technologies. And if you look at what NVMe is and you look at what NVMe over Fabric are, those two technologies are derived almost entirely from those kind of consortiums and take the technologies in there that are way out in the future and apply them to what we're doing today.
So the storage guy wants to ask you a question.
Okay.
So you mentioned NVMe over Fabric.
Yep.
You said that it can't handle failover today. Have they? This may not be a fair question to ask you because I know you don't sit on that, but you're probably pretty well in tune with it. Have they defined what that looks like and how to do failover, and it just hasn't been implemented yet? Because I thought they finalized that. I thought I heard they did that like a couple months ago.
So the NVMe over Fabric as a set of as a protocol goes through a set of ratification steps.
T10, right?
Yep. So, and it goes through the ratification steps. Now, the first step of failover has been ratified, but nobody's implemented it. But even then, it doesn't bring us parallel with where we are today. So there's still more work to be done before we can get there.
And that is a vendor consortium.
It is.
In fact, we have somebody that's on it.
We sure do.
It's not like we're not involved in what's going on with NVMe over.
Oh, absolutely. We're not only. I mean, I know the guy who sits on the board that we have. Yeah. So, and we are actively involved in doing this. Absolutely.
So, if I was a betting man, I mean, personally me, and I'm not as close to all this stuff as maybe you are, but I would think NVMe over Fabric is going to win. But it's not. Clearly, maybe it's a little too early to put all your money on that horse, but it's probably going to be the safe bet.
Yes, yeah, that's where I would put my money. Yeah.
Well, but you still have to consider that a lot of enterprises are going to need, like, not only the scalability but availability and be able to distribute these services over a wide platform. And the performance is fantastic for that capacity, but if you need more capacity or you need to distribute these applications to something that's on the scale of a full-size storage array, it's going to take a long time before a lot of enterprises can handle the jump from 10 or 40 gig Ethernet to 100 gig or going to, InfiniBand or anything to make this, widely available to get that performance and actually make it usable outside of small scope.
So you're absolutely right. And from a large enterprise, they're, as a general rule of thumb, and this is a sweeping generalization, it doesn't apply to all of them, they're generally the slowest to move from an infrastructure perspective. Because if you're talking about moving from 16 gig to 32 gig fiber channel, okay, it can be done. Generally, it's tactical. We'll do a switch at a time as they come up and we move from one to the other. If you're talking about moving from 8 gig or 16 gig fiber channel to Ethernet, that's huge because you can't just you can't just rip and replace your entire, you can't just take down your enterprise for the weekend, replace the entire infrastructure, and it doesn't, it's not doable. So when we're talking about moving to NVMe over Fabric, there's a much bigger challenge there in that the world doesn't change. We had iSCSI came in and has made an impact, and I won't say that it won't, but it hasn't replaced Fibre Channel in most large businesses because it's just too hard to move there. And the same way that FCOE, so Fibre Channel over Ethernet, was promised to be the next big thing because it was still Fibre Channel, therefore it's still interconnected, and it was going to be great because it was routable over IP and all these, but it hadn't happened because it's just too challenging to get there. So there has to be a real driver to do these kind of things. It can't just be because it's new and whizzy. It has to offer something that Fibre Channel can't in order for those big businesses to move there. It's just a base requirement.
One of the advantages, though, is that this can come in cheap enough and be enough of a brand new whiz-bang, like explosive performance thing for them to bring in and see that maybe they would actually
exactly. So there's most of the other technologies that have been out there haven't been different enough to really make the change worth it. And this is something that really is different and offers something fundamentally different. Because you're talking about a fabric that you can have potentially memory devices on, as well as storage devices on. You can be talking about an entirely different storage architecture to anything that's ever been built, with a huge number of advantages. So this isn't just an incremental step, this is a big jump. And that is a good driver to move to a whole new set of technologies.
Once upon a time, we had storage gateways and routers that would allow us to do
Fiber,
Yeah.
FCOE. Do you foresee that coming back in order to implement this into existing data centers?
So it's a good question, like a kind of bridging switch that's capable, like a multi-purpose switch, if you want, that kind of thing. I mean, it's an interesting idea. I genuinely don't know if there are any switch companies actually working on that concept at the moment, because you would... The NVMe protocol itself that is being extended from NVMe over Fabric doesn't define the underlying fabric. So it doesn't. So for example, there's the concept of NVMe over Fibre Channel, which is not the Fibre Channel protocol. It's the Fibre Channel physical infrastructure. There's also, I mean, there are some really crazy ones. So there's obviously NVMe over things like Ethernet, and there's NVMe over PCI Express, but there's also NVMe over TCP/IP, which is kind of weird because they're taking something extremely high performance and putting it over a very generalistic networking environment. Kind of weird. But if you want to be able to route and go across WAN links and that kind of thing, and you don't have dedicated links, then there's that opportunity. And the important thing there that I'm getting at is that means that you don't necessarily have to have a media converter to be able to achieve those, because the NVMe protocol is far more flexible than anything we've ever had before. So we may not require those kind of devices on the basis that it can be more flexible than anything else we've seen before. If you can run it over Fibre Channel, for example, it may be able to coexist with the rest of your Fibre Channel infrastructure. May. There's no guarantee there. So we may not require those devices. Yeah. Yes, not to recommend to run over your actual LAN. Yes, saw that a number of times when iSCSI came out and people just stuck their iSCSI network on their LAN. And anyway, so I think the thing I'm trying to get at, and I'll try and be as unmarketing-y as possible, is that we're trying to be this kind of we are being this pioneer of taking this set of technologies and applying them into storage devices in a way that kind of nobody else is. It's not just about putting NVMe in. You know, we could replace our systems with all NVMe, but today it delivers relatively little benefit. We built this in a lab with 3PAR, and I'm pretty certain that's been done across the board. And that if we just built a 3PAR out of NVMe instead of SAS, what happens? And the difference is kind of not much. The way that the 3PAR architecture works, where it's so kind of parallel, so you know the virtualization stuff means that we drive so much out of SAS today that NVMe gives us kind of really incremental benefits. But if we have the ability, I mean, we need to go there anyway, because as I said, the tipping point of drives is going to make that a necessity because they'll become cheaper. But if we start looking at combining SAM into our devices as well as NVMe, then you're doing something entirely different. Now, we've had a tech preview of this that we've talked about, and we talk about this kind of reduction in average latency. So our first endeavor into this is using SCM as an extension of DRAM cache. It's an easy extension, and it delivers a huge pool of memory that we can talk to for a fraction of the cost that it would cost us to do that in DRAM. And that means that we can start looking at reducing latency by putting more data in DRAM cache than we've ever been able to before. So we can potentially reduce the latency by 50%. But the kind of important one here that's actually often lost is the difference between this kind of orangey bar over here and down here. And the last I/O service without it is over here at 60 milliseconds, and with it is over here at half a millisecond. And that's a big difference, because you're then saying not only am I reducing my total latency, but my maximum latency, the time it took me the longest to respond to a request, has dropped from 16 milliseconds to half a millisecond. That's really massive. So that starts giving you an idea of the power of these from a performance perspective, what they can actually achieve. So it's not just late average numbers, but it's that kind of top number as well. So,
So, I mean, based on what you said, these technologies will be implemented pretty much in greenfield infrastructures, right? So,
okay.
What are the? I mean, because you're not going to rip and replace your network, you know. All good points. So what are the applications that are going to, what applications will inhabit that greenfield infrastructure?
So there's two sides to this. So one is taking NVMe and SCM and putting them inside a storage array, for example. Now that one doesn't require a greenfield site because you can apply that directly to any array. We're going to, for example, offer the cards and a bit of software update to make this happen on 3PAR. You can take an existing 9,000 or 20,000 series array, put the cards in, update the software, and you will get this on the existing array. No changes required to your infrastructure. So, and that's this thing that I'm kind of showing here. When you're talking about NVMe over Fabric, then you're talking about something different, because that is a rip and replace essentially of your physical infrastructure. Now, greenfield sites are the obvious ones to adopt that first, because there's no existing infrastructure to have to migrate. Instead, you can just put it in and, you know, off and running with that from the start. Now, if you're looking at that kind of approach, then anywhere where you're looking for things like density and performance, because NVMe over Fabric applies to solid state arrays. So if anywhere where you're looking at eliminating spinning media, those kind of things, NVMe over Fabric makes the most sense. So in a kind of entirely solid state data center, that's the kind of place you're going to be looking at it. But in reality, the idea is to use a technology like NVMe to replace Fibre Channel and to replace iSCSI and become the predominant storage protocol within the data center. So think more broad, think general purpose, you know, block storage devices, memory devices. And what you're going to see pretty soon is a new kind of set of storage technologies that aren't just block arrays that they are today, but something entirely different and something entirely new. So there's going to be a kind of shift in the way that we build storage arrays that's going to make use of a kind of fabric approach and allow the storage arrays to talk to each other using these kind of technologies.
Well, I mean, Intel's been talking about rack scale, you know, infrastructure for years now.
Yeah.
So is that? I mean, it doesn't seem like it's gotten a lot of traction in the industry. So I'm kind of curious what.
The problem is we live in a kind of, when you come up with a concept like that, that's kind of way out in the future, the problem is we live in a world of huge change. And by the time you get to that future, things have changed, and that future kind of is a timeline that doesn't exist because the world's branched and we're going off over here now instead. So I'm not saying that we're not going to do rack scale compute, rack scale storage. I'm not, you know, those are still things that we deliver. But the world's changing. You know, as Omar said, we have a whole new set of applications, a whole new set of services in the world that didn't exist when a lot of those concepts were come up with. And those have been addressed in different ways. So if we look at something like Scality sitting on top of Apollo servers, the idea is to solve the problem of scale by using discrete components and building up something that's greater than the sum of its parts. What NVMe over Fabric does, for example, is allows us to take a similar concept, but built on a brand new set of technologies for your entire storage environment. So imagine a world where you might have a fabric, and some of the components on it are initiators, some of them are targets, some of them are pure storage devices that are consumed by other devices on your network, which then provide services out. So think of it as more a one huge set of infrastructure that all work together, rather than the way that we build fabrics today with a storage array, then a fabric, then a host server, and then a fabric, and then a client. Think of it far more collapsed down than that. That's what these kind of technologies are going to allow us to do in the future.
Well, operating systems like Windows Server 2016 already utilizes storage class memory.
So it's a good question. So there's challenges with storage class memory in that it's a new paradigm that we've never used before. So none of the applications know how to use it, and none of the operating systems know how to use it. Because as far as they're concerned, they just see a memory device and they'll just read and write to it like memory. But that means that after a power off, when they come back up again, they'll just assume it's blank and write to it again because they don't know how to interact with it. So that means you need support from the operating system. So whether that's Windows, Linux, Unix, but also VMware needs to know how to talk to this kind of technology. And then even once you're in that kind of world, that gets you half the way there. But your applications, so if you want to be able to accelerate Oracle, for example, that application needs to be able to understand that it can use this as memory, but it doesn't have to worry about it not being there. So if the application is shut and is brought back up again, that data still exists there and it can still access it. So there has to be a shift in all of those parts to be able to make use of it. That's even just in a server infrastructure. So when you start looking at a storage device, and the storage device may be offering out memory as well as storage, that's a whole new shift that you then have to adopt again.
So with server class memory and NVMe and all that, I mean, obviously right now with SSD, we're basically punching through holes and using it up, and so we do garbage collection.
Yep.
I mean, so when we go into NVMe, we still have that server class memory. Do we still have to do garbage collection because it's still a flash?
So it's not NAND flash. It doesn't behave like NAND flash.
Okay.
So there are some devices out there that kind of pretend to be storage class memory that aren't really, that are actually NAND drives with huge amounts of memory or bandwidth or whatever it be, that kind of pretend to be something that they're not. But the genuine SCM technologies, the first iteration today, offer a significant performance increase and a slight bump in terms of things like endurance and those kind of things. Now, as we get further and further down the world, so as we have the second and third iterations of Optane, a lot of those kind of concepts just disappear because the underlying media doesn't require any of the things that NAND does. Now, the first implementations are kind of like think of them as fully functional tech previews, and the technology works, you can use it, but it's not the end goal. It's just the first iteration of what that's going to be. And as the world progresses, we're going to see much faster, much higher endurance technologies coming out of things like Optane. And at that point, things like garbage collection will be completely a thing of the past.
And then a stupid question. Do you think we'll ever see spin torque memory as a reality?
There's so many of these, and the one I get actually most asked because I work for HPE is Memrista. Like, will it ever exist? And spin, so there's a lot of these. No comment. I'd love to see these kind of things. And we've been talking about Memrista since, I don't remember when, 2000, and there are, with each one of these technologies, there's a challenge with getting it out. It's not that easy. I mean, IBM had an equivalent, I can't remember what it was called. We've had Memrista. They all work in the lab, but there's a challenge of taking that technology and bringing it out to full-scale production. And that is where things become much, much more challenging. Will we see them? I hope so, but I can't tell you for sure.
They talk about years of transferring to biological models.
Yeah.
Storage.
Yeah.
Look how efficient DNA is, right?
Yeah, absolutely. Potentially tens of thousands of years for something like DNA, but how do you make use of that kind of technology? It's a big question. There's a huge amount of work going into it. So I don't know how I'm doing for time, but I'm probably way over at this point. So I'll just carry on until someone stops me and I get the, that kind of sign. Sorry? I've still got 15 minutes left. Oh, well, I'll take my time.
More than just shoving in new parts and say, hey, look, it's fast.
Yeah, exactly. And so the thing is, we could just, ram SCM cards into the array and say, yeah, it's much faster than it was before. But
the vendors have done that.
But the thing is, if there's potentially so much more you can do with this technology. There are lots of different examples of how we could use this, and I'm not saying any of these are kind of set and that we're going to do this kind of stuff, but just if you kind of think about the way you've got this. If you've got an actual memory device that you can talk to as if it's memory. So from my perspective, from inside a storage array, inside the actual operating system, inside the storage array, if I've got a memory device that I can talk to that doesn't lose data, I can start thinking of all kinds of applications for that. Now, not only could I offer memory over a fabric that a server can write to, persistent memory over a fabric, so those are some kind of things we have with NVMe over fabric, but inside the array, every array in the world has things like metadata. So, data to do with the volumes, the structure of the array, that kind of stuff. For the CPU to have to interact with it, it has to have access to it, so it has to be in memory. But there's a really limited amount of memory you can fit in a storage array, because we need so much for things like data cache and those kind of things, that there's not that much left over for the actual OS to run. So most OSs are very slim and have a tiniest memory footprint possible. So that means that if I want to have access to metadata, we have to page in and out. Every storage vendor has to do this because your metadata is so huge, you just cannot hold it in memory. But if you've got an SCM device, a memory device that's persistent on the memory bus, I could look at sticking my entire metadata structure in there and have access to it. That means I don't have to page in and out. My CPU has direct access to my entire memory structure. That means I can do some really awesome stuff in terms of not just accelerating workloads. That's great, we can do that. But it means that I can start being very clever about the data. I can start doing not just real-time analytics, but I can start being more intelligent with the data because I've got such fast access data to the actual data and all the metadata. So I can start sort of coming out with a whole new paradigm of how we enable data, not just storing it, not just making it faster, but actually doing something with it other than just serving it up. And that means I can open doors to a whole new set of different technologies that you're able to offer as a storage array. And that's where the world kind of really starts changing, is that when you start looking not just at making an array faster, but making it fundamentally different, that's when you start doing something entirely new, entirely different. And that's when your greenfield site starts becoming something far more than just a faster storage array, but a far more intelligent infrastructure end to end. So, I mean, in terms of the actual technologies that we have, I've talked about, I think, nearly all of these. The big red herring I haven't really talked about is QLC. And so when NAND first came out, we had what was called single level cell, the first drives. They were eye-wateringly expensive. We had a 50 gigabyte drive, which sounds ridiculous now because I've got a USB key that's bigger than that. That thing was about the same price as a small sedan. So these were kind of, you bought as few of these as you possibly could. And today we're in the world where for the same kind of money, I could buy 16 terabyte drive, maybe bigger. So there's been a huge change in kind of this first end here. I've talked about NVMe and I've talked about SCM and kind of what they are and what they deliver. One of the things I haven't really talked about is QLC. And QLC replaces, replaces perhaps the wrong word. It kind of adds to the technology we have today. So we've had single level cell and then we had what we call multi-level cell, which is a bit of a misnomer. After single it was multi, but it's two. It's dual level cell if you want. That would be a more modern name for it. What those things mean is you can increase density. So the more bits of data you can store in the same physical footprint, the higher your density goes, because now I can double my data density. But with that comes a reduction in endurance and a reduction in performance. So there's kind of a handoff with those. And TLC, which is where we kind of are today, which is weirdly missing from this, is triple level cell. So that increases the density again, but it has the same impact on performance and endurance. Now that's fine because SLC drives are so fast and have so high endurance that you can't actually make use of them. We've got drives out there today, even today, that are MLC devices that have been running in arrays since 2010, 2011, and they still have 100% of their life left. They've been battered in an enterprise environment, and they're still at 100%. They haven't even been worn down by 1%. So the endurance on those from a storage array perspective is actually too high. And that's why we're easily able to adopt things like MLC and TLC. Now, when it comes to TLC, you have to start thinking differently because the endurance is quite a bit lower. And we had a whole set of technologies in both 3PAR and Nimble to be able to make more use of those drives. So to be able to extend their endurance using software and improve their performance, again, using software. Now, QLC goes further and allows you to store 4 bits of data in the same bit of space that we would have stored 1 bit of data with SLC. So they have a 4-time density improvement. This is where you start looking at those kind of 60 and 128 terabyte drives. But they change everything. They change everything from the performance and the endurance they offer, but also how do you protect 128 terabyte drive? If it fails, you're potentially replacing 100 terabytes of data, and that takes time. It's not easy. So you have to completely rewrite the book on how you protect the data stored on those drives, because it's not just easy as stick RAID on it and if it takes 3 weeks to rebuild that drive, what are you doing in the meantime? How are you protecting the rest of the data? So there's a whole shift in not only how do I get the performance and endurance out of these drives, but how do I protect the data sitting on top of them? So when you combine these drives that don't offer that kind of performance with this media that does offer extreme performance, now you're talking about real density. So those people who want petabytes in 1 or 2U, now you can hit that capacity point with QLC, and you can use technologies like SEM on top of that to provide the performance that you need. Now, I'm not suggesting hybrid. Nobody wants to be back in a hybrid world. Nobody wants to be managing auto-tiering and all that kind of stuff, because we've only just left down. I don't think anyone's got an appetite to go back there. But if you're looking at a fundamentally different architecture that's able to take advantage of the advantages of both of those technologies and build something very different, then you've got high density and high performance. And that is very, very different. I've said about SEM Plus and I've said about NVMe over Fabric, so I'm not going to repeat those. In reality, though, I think the thing is there's going to be a huge change in what we do. It's not just a matter of the next increment. It's not just a small change. We're not talking about moving from SCSI to SAS, which just takes a parallel protocol and makes it serial. We're not talking about moving from SLC to MLC, which is a slight improvement in density, that kind of thing. We're talking about a big shift in performance. We're talking about efficiencies that we've never been able to achieve before, because the whole way that we handle data in this kind of architecture is just so fundamentally different. And obviously, it requires a huge amount of innovation because, as you said, you could just ram a whole load of SCM devices inside a storage array and say, yeah, it's really fast, but you haven't done anything really. So you have to think outside the box in entirely new ways to do this. And from my perspective, then that kind of means that we have to kind of really define what the future is going to be. It's out there to be grabbed. There's no definition of what these things are yet. We've got lots of different ideas across our entire business of how we can apply these. Everywhere from the guys in the server team telling us what they can do, from those of us in the storage unit to try and work out what it is we can actually offer. How can we change the entire landscape to do something that's never been done before? And there's a lot of partnership here because there's such a big opportunity to change things and offer something brand new that I want to make sure, we all want to make sure that as we do this, we work in partnership and build something that works across the platform. So when we bring technologies like SEM into our storage architecture and into our platforms, that we build something that works across the platforms, not just building something different. So you're going to see these kind of technologies leveraged in the different platforms like Nimble and like 3PAR. And you're going to see these working to complement each other directly. And you're going to see that a lot kind of going forward. And then as we adopt these things across some of the other areas as well, you're going to see a lot more kind of tight, close partnership as we build something that's kind of very different. I think that's where I end because my next slide is black. So if you guys have any final questions.
So, one of the big differences in the industry now, as opposed to 20 years ago, is that a lot of the R&D, the really advanced R&D stuff, is being done by a few vendors, and it's not being sold to the public. It's Amazon and Azure and Google and Facebook, and they all have somewhat different approaches and. Facebook is doing the open compute thing, and so a company so they're working with warehouse scale computers, hyperscale, right? And I know you guys probably do some supplying to those guys, but there's this fundamental difference in scale where you're still focused on enterprises, which are a couple of orders of magnitude smaller than the hyperscale guys. So how does that, do you see any, comparative advantage, or advantages one way or the other between those issues of scale?
Yeah. So, I mean, they're very different scale. If we look at the hyperscale guys, they have an entirely different set of challenges to the kind of challenges that our customers generally have. Because you said there's orders of magnitude difference. If you're building a cloud platform for the masses, the very architecture of what you have to build, from the physical hardware that you put in there through to the software that brings everything together, has to be totally different. But they also kind of have the luxury in that they're not inheriting a lot of the historical architecture. So they don't have to worry about how they're going to put specific applications in their environment, because they're not going to exist in their environment. What they're building is something totally new. Now, they all have the same issues, but they've all tackled them in different ways. A lot of the innovation that exists in there is usually fairly specific to the issues that they're trying to solve. Whether that might be a file system or a management system, whatever it might be, they don't really apply directly to your average enterprise because they don't face the same issues. But that doesn't mean we can't learn from them. And there are some things that have been developed inside those kind of organizations, kind of concepts and things, a lot of which is unbelievably open. So we are able to adopt some of those kind of things. And so that gives us opportunities to take the technologies that do apply to enterprises, whether that might be something on a fabric, whether that might be something way down low level that runs inside a server or a storage array or a switch or whatever it might be in between, and take that kind of concept and bring it to an enterprise market. So in the same way that I use the analogy of Formula One cars, kind of this being this proving ground for a lot of new technologies, those kind of hyperscale guys offer us another way to look at how issues have been addressed and how we can apply those in the enterprise as well. Usually in a slightly different way that either makes them more appropriate or just for the sake of getting in the price that those kind of guys might need. Because not everybody needs to buy servers and 10,000 at a time. So how do you manage servers at scale? That's a problem for the hyperscale guys. If you're a big enterprise, that's a problem for you as well. So what can we learn about how those guys are applying management to that kind of size infrastructure to our enterprise customers to bring something fundamentally different for them as well, to be able to manage their environment? Because sure, Google might have a billion servers, I've no idea how many they have, and they have to be managed. Now they have a bigger team than your average enterprise, but the scale is way off the chart. But that doesn't mean an enterprise with 1,000 servers that's being managed by 2 people don't have the same kind of challenges. The scale is just different. So how can you take that concept and bring it to that customer to deliver something different? It's going to happen within storage, it's going to happen with management, compute, you name it. It's going to happen everywhere.
As a user for Hewlett Packard Enterprise, we have one of the challenges we face. Talk to your customers. Most of your customers are state of the art. I mean, state of practice more than state of the art.
Yeah.
And so, getting them to make that shift
can be a challenge.
When you start now, I mean, there's the enterprise, but then there's a whole bunch more of those SMB people out there that are very important to the market because there's a lot more of them.
Yeah, you're absolutely right.
There's only 100, top 100.
There's only 100 top 100s, yeah.
And the problem with that is some of the tools are so complex, and the time it takes to configure those tools for a half a dozen machines, you're better off just doing it by hand to begin with and saving time.
And I'll use an example from our own past that feeds directly into that. Is that we have had historically a tool called Systems Insight Manager. Don't know if you guys have played around with it. Beautiful concept, and it delivered some really kind of awesome stuff. But it was, and I used to be in a different life. I used to be an installation guy for Systems Insight Manager, so I used to go out there and install it, and it was a nightmare. Any bit of software that takes 4 hours to install is kind of crazy. So I've been there and I've worked with it. If you are a huge enterprise, there are a lot of advantages to it. If you had 4 servers, not so much. Now there were those guys out there with 4 servers who put that stuff in there, and it delivers some benefits, but they're kind of limited. And simplicity has driven a lot of how the world has changed. If you look at everything from how you interact with your laptop, your phone, the world is very, very different now. the expectation of a user to be able to just pick anything up and use it has changed how things work. So you're going to see a drive to simplicity, whether that is to be able to enable a larger enterprise to manage at scale, or a very small customer to be able to manage their environment without really knowing what's going on inside their environment. And we've actually relatively recently released a set of technologies that allow customers to perform performance troubleshooting without having to understand performance. And that's very, very different, because today, if I'm a storage administrator and I want to troubleshoot performance, I have to know my box inside out. I have to know what all the definitions are. I have to know what all the acronyms mean. I have to know what everything is relative to each other. I have to understand all the different resources in my storage array and how to address them and how to identify which one's wrong. But if we can give you a way to be able to troubleshoot performance without understanding any of those things, that changes the world for those guys, not just enterprises, but the smaller guys, because now they don't have to be storage experts. And that's the world that we have to head towards, and that is exactly where we're going at the moment. Driving the simplicity to be able to manage anything without having to actually fundamentally understand what's going on under the hood. So there's going to be a lot of that. There has to be. Okay, I think I'm going to finish almost dead on time as well.
Yeah, and I was going to say you are dead on time, so we have a 30-minute break